ANSYS Simulation, Lecture 8, Part 1, Steady-State Thermal Analysis. We can draw a 3D model and then make sure that the software is loaded. And it is loaded. So we will enter ANSYS workbench. And this is the schematic interface for ANSYS. And there are two types of steady state. And the second is transient thermal analysis. And we'll choose steady state and drop it on geometry. And for the material, I need to change from structural steel to aluminum alloy. So I'll enter material interface. And in the material library, I'll choose the general material and include or add aluminum alloy to the problem. And then I go back to project. Now we'll enter ANSYS mechanical for the thermal analysis. And this is the steady thermal analysis. By steady state, we mean that the time goes to infinity and the system reaches thermal equilibrium. So the temperature does not change anymore. So if you fix a point somewhere in the component, the temperature is fixed with time. So that is called steady state thermal analysis. So we'll wait for ANSYS mechanical to open. Okay, this is ANSYS mechanical, and the first step is to draw a 3D model, right? And then open a study. So this is the step 1, the geometry. And the step 2 will be the material here. We'll change it to aluminum alloy. And then step 3 will be mesh. I'll update the mesh using default mesh. And for step 4, the initial temperature is not really important for steady state analysis, and the time is also not important because steady state means time goes to infinity and the system reaches thermal equilibrium. So for the step 4, we only apply the heat source, which is heat flow, not heat flux. Heat flux means heat flow divided by area, so we define heat flow on the bottom surface of 28 watts. So this is the loading. For the boundary conditions, we define convection on all surfaces. Select all, except for the bottom surface, which is the heating surface. So apply. We have 156 surfaces. All the surfaces in contact with the air must be chosen. And the convection coefficient is 10 watt per meter. Make sure that the unit is right. 10 watt per meter square scale. Meter square, degree C or degree K scale. So that is very important, that the stagnant air condition convection coefficient is 10 and the ambient temperature is 25. And there's a problem with this 10 because when the columns are closer and closer, actually the convection coefficient will drop from maybe 10 to 8, even maybe to 6. So this is the major problem of theoretical aspect of solid state thermoanalysis. In other words, the convection problem, convection coefficient is a major problem in solid state thermoanalysis. Okay, now we will choose temperature as the result, so that the system calculate. And then we'll probe for the temperature at the top of the center column. So now the temperature, first of all, we'll make sure that the temperature is degrees C Celsius, and it's easier to read than degree K. So we can probe for the temperature maybe at the center, which is 96 degrees, right? It is the temperature at the center, okay? 96.25 degrees. So this is the temperature when the system reaches thermal equilibrium. And we'll run transient thermoanalysis later. So we'll confirm that the temperature will rise from 25 to 96.25 at the time sufficiently large.